Hi, this is Nathan Tintle. In this Learning Goal video, we're going to talk about how to apply simulation and theory-based methods to samples from populations, and we'll use the data from the Supersized Drinks poll. When we sample from a finite population like all New York City voters, we can use the same methods as what we learned earlier for an infinite process. For example, in the Doris and Buzz study, we consider the parameter there to be the long-run proportion of times that Buzz pushes the correct lever. This is a sample, 16 observations, from an infinite process. Doris and Buzz could sort of go on pushing levers forever. Contrast this with the kind of data we're looking at now. Now we have a sample from what we call a finite population. There is a group of New York City voters. It's a finite group. We could potentially write down all of their names. It's a very large group, but it's finite, unlike that process, which is infinite, where Buzz and Doris could sort of push levers forever. The difference is subtle, and as we'll talk about, the implications are actually rather minimal. As long as the population is substantially larger than the sample, people say 10 to 20 times as big, then the methods we use to test hypotheses about a process can be used for a sample from a population. In particular, we could simulate that null hypothesis, or we could predict the null hypothesis using a theory-based approach, as long as those validity conditions are met. Let's take a look now at the one proportion inference applet. You can see here that the way we conduct this simulation and the way we get a theory-based p-value is exactly the same as we would have done earlier in the course. Specifically, the probability of heads is the null hypothesis proportion, in this case 50%. The number of tosses is equal to the sample size, 1093. We conduct many repetitions of the simulation. We can generate a p-value by saying how often do we get a number less than or equal to what we observed in the study, 0.46. Doesn't happen much, that's our p-value, 0.006. Similarly, because the validity conditions are met on this data, we have at least 10 people in the sample who said yes, they're in favor, and at least 10 who said no, they're not in favor. We can use the normal approximation to get a p-value as well. A couple of words of caution. First, some students mistakenly think that small sample sizes are better to make sure that the population is at least 10 to 20 times the sample size. That's not necessarily the case. If you are taking a random sample, then bigger samples will always yield better results. The issue here is that the models we're showing you, where a population and a process can be considered essentially equivalent, only work as long as that population is substantially larger than the sample. If that's not the case, there are more advanced statistical methods you could use, and you can learn about those in another course. Secondly, this whole population to sample size ratio, the 10 to 20 times thing, is really irrelevant for a process because a process is infinite. And lastly, in practice, the differences between processes and populations in terms of the way we analyze the data really don't matter too much.